All right, here's just a quick video about the homework problems we weren't able to get to yesterday and today. One was 3-69 about the sum of two numbers is 60, and it says determine the numbers so that their product is the greatest. So anytime we have two situations, it's getting two variables, and we want to get it into one. So for example, x plus y equals 60, and then we have the product. So x times y equals the product. Well, I can make y in terms of x just from this equation here, like y is 60 minus x. So if I multiply those two together, I get a function that's in terms of x. So I can actually find all of the products. If I notice this is a quadratic, it's actually an upside down parabola here that you're going to have zeros at 0 and 60. So that the vertex, the line of symmetry, is at 30 and the product would be 900. For 79, I just did A and C, but essentially you're just doing U substitutions. So you substitute with the U and then see if you can factor anything individually. For example, in A, it looks like U squared plus 3U. Well, I can factor a U out of those first two terms, and then I plug back in what I said U was, which was 2x minus 1. And then just add anything, simplify from there. For C, was a little bit bigger, but I have U to the fifth plus 4x U cubed. And then I factor out what I can, which is a U cubed, and I get this U squared plus 4x. Well, eventually it gets back into x's, so then I can combine some of those like terms. So I get 2x minus 1 cubed, and then I expanded the 2x minus 1 squared. So make sure you get middle terms, 4x squared minus 4x plus 1 plus 4x. And then those middle terms go away for that middle portion there. Next was a step function. So we said sketch just like a piecewise function we had before. It's just saying the line at 5. Okay, so I just have a horizontal line at 5 from 2 to 4, at 3 from 4 to 5, and then 8. So this is getting to that idea of area under the curve. So we have the shaded regions all the way below this. So rectangles, which we'll use rectangles with kind of curved lines as well, but just find the dimensions and add those up. 96 was dealing with some average speeds. Now, an average speed is just the total distance they went over the total amount of time. Now, this one was a little bit tougher because we didn't know the distance, so we had to just keep it as a variable. So I've made x the distance to the coffee shop. So it looks like then she's got to go to and from the coffee shop, but how she went there is different on her trip. So the total distance is 2x. Now, the total time is if she went a faster rate early on, we have to compensate for that distance. Right? It's going to be shorter. And then when she went a little bit slower, it's going to take her more time. And that's why we have this total time equation as x over 45. That's her distance over time. That's her speed plus her other speed, distance over time, but we just don't know the distance. So if I want to find the average speed, I just divide these two, the total distance divided by the total time. Now, I didn't simplify this, but this would be good practice to simplify those complex rationals. It's got fractions. You can find a common or multiply by something so it breaks or busts the fractions. And it simplifies. Eventually, I think it's 30 miles per hour. And lastly, 106 is just Lou walks every day. He's going 4 miles per hour. So it's another good practice, an intro to area under the curve. So he's a constant rate for an hour. And we just want to know with these, the domains and the ranges, what do the dimensions tell us? So, if this is in hours and this is miles per hour, I can break this up into rectangles and see how far he's going. But eventually we know that he went 4 miles. Hopefully this helps. Let me know if you want to meet individually.